Hello everyone. Welcome back to the next lesson in the quantum physics series. In this lesson, we will be talking about wave-particle duality. What is wave-particle duality? By definition, wave-particle duality means that a particle can be a wave, and a wave can be a particle. But how is this possible? How can something be two things at once? Let's begin our journey through wave-particle duality. To start, let's remember how particles and waves move. Particles move with a specific speed to a location, while waves travel with amplitudes and frequencies. Waves do not travel in all directions, but in the cases of water and sound, they do. In order to understand more about wave-particle duality, we need to learn more about waves at a quantum level. It turns out that light is a wave, and it also appears at the quantum level. Light has most of the properties which we learned about. Light has an amplitude and a frequency. The frequency of light determines what color it is, and the amplitude of light determines how bright it is. But what is a wave of light, and what is it made out of? For this, let's look at a flashlight. When the battery has more electricity, the light shines brighter. Since we already know that the amplitude is how bright the light is, we know that the amplitude is also the energy of the light. Now let's look at a phenomenon. This phenomenon is called the photoelectric effect. What happens when you shine a light on a material? In our world, the material will get warmer. But in the quantum realm, the material starts to release electrons. The flowing electrons release energy in the form of electricity. With this information, it is easy to conclude that light is a particle, because waves don't transfer energy when they collide with particles. They get bounced off. This is extremely similar to a particle. This very phenomena started a decades-long debate about the nature of light, and in short, Einstein won it. But there's only one small problem with light being a particle. This phenomena only works for certain frequencies of light. Increasing the intensity of the light doesn't make the material lose an electron. If light was really a particle, then its behavior shouldn't change with a different frequency. Remember, waves have frequencies while particles do not. Einstein won his Nobel Prize for explaining the photoelectric effect. He theorized that light was both a wave and a particle, as a thing he called a wave packet. We will call this wave packet the photon. With this explanation, he proved that light can be either a wave or a particle. This showed the dual nature of light. In the 19th century, a physicist named Thomas Young created an experiment to test whether light was a wave. In his experiment, he made sunlight travel through two narrow slits. If the sunlight was a particle, then there would be two distinct lines of light behind the slits. But if the light was a wave, the waves of light would interact with each other as they went through the slits, and they would create an interference pattern due to the diffraction of light, as we saw with the water before. Once again, the diffraction pattern is what happens when the light travels through the opening, and the interference pattern is when the two waves interact. So you get a result like this. The pattern on the back showed that sunlight was a wave. Since we know now that light is both a particle and a wave, can a particle like an electron be a wave as well? Young's experiment, the double slit experiment, was repeated again with electrons instead of light a century later. This experiment found the exact same thing. These experiments helped prove that waves and particles were similar. It proved wave-particle duality. The experiment yielded powerful yet confusing results. This experiment changed modern physics and invented quantum mechanics. Although this topic is very confusing, it does not occur at our level. But I promise, if you think about it, it will all begin to make sense. Tune in next time as we go deeper into the heart of quantum mechanics.